Ready for Navier-Stokes? Okay. I had a starting page and I've moved it all the way down here. No, I didn't have it. I'm getting a little sloppy as the semester progresses. Okay, but we can write the Navier-Stokes equations for this situation. We assume 2D flow, right? We're going to assume 2D flow. We're going to assume steady flow. And in a laminar, if it's steady, it has to be laminar, right? Because if it was turbulent, it would never be steady. And we're going to assume incompressible. So before we cancel out terms, let's write them out. But just for 2D. So for 2D, our continuity equation is du dx plus dv dy equal to 0. And since it's 2D, we only have two momentum equations. And we have our acceleration, rho, and it's steady. So I'll not write the partial with respect to time because it saves us some writing. But I will write all the other ones. So we have u du dx plus v du dy is our acceleration in the x direction equals to minus dp dx and the viscous term plus mu, the Laplacian of u, the first component of velocity, now the other equation, rho, and we have u ddx plus v dy, but of v now, and the pressure gradient in the y direction and our viscous term with the Laplacian of v. So we've written the Navier-Stokes equations enough times that now it should almost be natural. And what are the boundary conditions? Well, the boundary conditions for this situation are, of course, no slip. So u is equal to 0 at y equals to 0. We choose our y coordinate to coincide with the flat plate. We also have what's called the no-through boundary condition. The flow cannot go through the plate. So v would be also equal to 0 at y equal to 0. And we have unperturbed flow at infinity. The flow is unperturbed when y tends to infinity. And so that must be the free stream velocity u0. So even though we have the full set of equations there, the full set of equations and boundary conditions. And assume 2D flow, steady, incompressible. And even under these circumstances, already for this flow, there's no solution. We can't really write directly from there, we can't just write it out like that. We have to still make a few more approximations so that we can get a solution. So what are the approximations that we're going to make? The assumptions. So first of all, we're going to say the flow is mostly in the x direction, and the flow in the y direction, the component of the velocity in the y direction, we're going to assume is very, very small, so small that it's negligible. So we're going to say v is much, much smaller than u. The velocity normal to the plate is small. That makes sense, right? very small. We're also going to assume that the variations of everything in the normal direction dominate, in the sense that d dx of whatever is much, much smaller than d dy. So variations, normal, to the plate dominate. So basically du dx is much, much smaller than du dy. The u velocity changes more in that direction by the effect of viscosity that it changes in the direction of the plate. And also for the second derivative we can do the same, or for the v. v, for example, variation with respect to x is much smaller than v variation with respect to y. And so now we can apply these new assumptions to the Navier-Stokes equations. So for example, let's see, what if we look at the y momentum equation? We look at the y momentum equation, and we have here dv dx, that's very small. Then v is very small, so this is small. Then this one is very small, it's very small, because all of the derivatives with respect to x are small, and even the second ones, and also v is small, so all of this is very small. And, well, v is very small, so this is also small. So we're only left with, basically from the y momentum equation with these assumptions, we're only left with dp dy is equal to 0, approximately equal to 0, with our assumptions, which means that p is only a function of x. So basically the y momentum equation can be neglected entirely now, and the pressure can vary only along the boundary layer. And in fact, one can consider the pressure to vary like in the inviscid unperturbed flow, since it doesn't vary in the y direction, and within a certain distance of the plate outside of the boundary layer the fluid is inviscid, then the inviscid pressure applies. Bernoulli's equation. I can do Bernoulli's equation in the inviscid area, in the area where there's no viscosity, say, and so the pressure is going to be known. Basically, the pressure completely drops out of the whole discussion from now on. Does that make sense? It varies only in the x direction. In the y direction, we can assume it to be a constant. Somewhere in the y direction, the fluid is unperturbed and inviscid. So the pressure there is known by Bernoulli's equation. So it's known everywhere. Right? Do I need to say that again in a different way? You're looking at me a little bit confused. Once more? Once more to solidify it. Okay, dp dy is 0. So in this direction, p is constant. It only changes in the x direction, right? The boundary layer is very thin, and all the viscosity effects are in this boundary layer. Outside the boundary layer, somewhere in a large enough y, the fluid can be considered completely inviscid. If it's completely inviscid, I can use Bernoulli's equation to find the pressure, and therefore pressure essentially is known from the conditions at the unperturbed locations. We could find them. In fact, for the flat plate, if the streamlines are completely horizontal, the pressure is constant, and the pressure for a flat plate is constant everywhere in the boundary layer. It would only change. There would only be same variations in the pressure if they were curved streamlines, for example, if the flow was going around an airfoil or something. But for the flat plate, the pressure is constant everywhere in boundary layer flow. It drops completely out of the unknowns. Okay? So this is the power of the approximations, that all of this came to Prandtl in some incredible insight. Okay. So I have not yet. So let's say we say that the y momentum equation completely drops out. And the pressure can vary only along the boundary layer, and for a flat plate is constant. P is equal to P of x. And for the flat boundary layer, I'm going to abbreviate BL because otherwise I would write it too many times. Pressure is equal to a constant. So what do we have finally for our Navier-Stokes equations with all of these additional assumptions? We have continuity. We never can get rid of continuity because mass has to be conserved. And so we have continuity. And only the x direction. And for the x direction, remember, P is going to be a constant for the flat case. And so pressure drops out. And I'm going to just divide it by rho, so I'm going to get on the right-hand side, I'm going to get nu instead of mu. And I have a convective acceleration term u du dx plus v du dy is equal to nu second derivative of u with respect to y, only because the with respect to x is much smaller. Yes?
Sorry, it would help if we define the axis in that first drawing. I think I was assuming wrong.
So this is the flat plate.
Yeah.
And y is in this direction and x is in this direction.
We're assuming z is vertical.
No, y is vertical. There is no z. This is 2D.
Right, it's 2D.
So this is the simplified Navier-Stokes equations for the case of the flat plate boundary layer. We assume pressure for zero pressure gradient. And they look like they've been simplified quite a bit, but in fact, there's still no solution. They're still very hard to solve, and the reason is that they're still nonlinear. We still have the nonlinear effects here, and we're still stuck. Really. No, very difficult to solve. So, how did we make any progress in boundary layer theory? It happens that a student of Prandtl, his name was Blasius, came up with a very clever idea of that allowed him to get to some solution. His idea was that basically a similarity argument. He argued that the boundary layer profiles should be similar in shape regardless of your location along the plate. So, for example, if I'm looking at, so this would be the limit of the boundary layer. We're still laminar, remember? So if I look at the shape of the profile here, and I look at the shape of the profile here, they should be similar. It's just stretched out a little bit, was his argument, but they should be similar in shape, which sort of makes sense, right? All that happens as you move along the boundary layer is that things get a little stretched out as delta increases, delta being the thickness of the boundary layer. right? This is here the level of delta. So this argument means that the velocity, the relationship between the actual velocity of the fluid to the stream, the free stream velocity, is actually a function, an unknown function, call it g, of y over delta. So you can non-dimensionalize the problem. G is still an unknown function, but these are dimensionless variables now. And believe it or not, this allowed him to use a change of variable that converts the partial differential equation into an ordinary differential equation, and he could solve this, not analytically, he could solve it numerically, but he was able to get to a complete closed form solution. We'll just sketch it out a little bit. Delta, sorry, it's delta, the thickness of the boundary layer. Similarity arguments like this are actually very powerful and they've been used in fluid mechanics for obtaining many approximate solutions. This similarity argument that the profile of the velocity is actually only a function of y over delta, where g is some unknown function, and then Blasius was able to do some arguments. Blasius did some dimensional analysis and did some arguments referring to the respective orders of magnitude of the different terms in the Navier-Stokes equations. And obtained, so I'm just going to kind of quickly get to some of his results by this clever change of variable, that delta, the boundary layer thickness, is actually proportional to nu x over u to the power 1/2. The boundary layer thickness grows as the square root of x and inversely proportional to the square root of the velocity. He just did some balance between friction and inertial forces and was able to get to this result. So then he used a change of variable and instead wrote the whole equations in terms of this new variable, and he was able to obtain the stream function, and substituting the results back into the governing equations, he was able to get, through all of this change of variable, he obtained an ordinary differential equation for eta instead of a partial differential equation. And then he was able to solve that ordinary differential equation numerically, and he found a profile of the velocity for the boundary layer, and he plotted this one curve, just one curve, because it had the shape of u over capital U doesn't change along the boundary layer. It only stretches out a little bit. So if you can actually do a plot, just one plot. This is the power of non-dimensionalizing. You were asking me the time. You can just in one plot have the shape of the velocity profile at any station, but it's non-dimensionalized by, in this case, y over delta is your non-dimensional variable. So he was able to solve this numerically, and obtained U over capital U naught, the actual velocity profile. And once you know the velocity, everything is known, right? He was able to obtain then a solution for, I'll write it in the, I think I have a picture of the actual profile, how it looks. Let me just take a snapshot and give you a few seconds. Okay, and here it is. He was able to plot the boundary layer profile and obtain a solution, for example, for the boundary layer thickness. He obtained delta boundary layer thickness is equal to, delta over x actually equal to 5 over the square root of the Reynolds number, local Reynolds number. These are the results he obtained. We've defined Reynolds number already. Then he was able to obtain shear stress once you have the velocity profile. You can get, you have the velocity profile, the gradient, the u dy, and once you have that, you can get tau, the shear stress, and so then you have the drag on the flat plate. So everything is known with these approximations. So that's quite remarkable, actually. The solution gives him the shear at the wall, and let me just write down the answer is, there's some constants here that appear from this numerical result that he obtained. Shear at the wall is 0.332, velocity to the power 3/2, and square root of rho mu, I don't know why I changed to rho mu here, over x instead of nu. So shear stress decreases with increasing x. That makes sense because as you go along the boundary layer, right, the boundary layer is becoming thicker, and so the velocity gradient is less pronounced, and so the shear stress must be less because viscosity doesn't change, and so the shear stress gets less and less as you move along the boundary layer. And also it varies with a certain power of the velocity. Yes?
Say that one more time. As you go along the,
yes.
go along the x, the boundary layer gets bigger.
Yes.
And
So
the velocity.
the velocity gradient here is less pronounced than here, where it has to go to 0 much more quickly, right? And remember, tau was in our Newtonian fluid was mu du dy. So if the u dy is smaller, because here it's smaller, it goes to 0 much more gradually. Near the leading edge, it has to go to 0 very quickly. So the slope, the gradient is very high, and so the shear stress is very high. So as you move along here, the shear stress decreases. Now at some point along the wall, the boundary layer is going to become complex. The flow develops different, it becomes turbulent, and so when it becomes turbulent, what you have is lots of different eddies of different sizes which transfer momentum. The transfer of momentum is much more efficient in the turbulent case. And because the transfer of momentum is more efficient in the turbulent case, the turbulent boundary layers are generally more compact. So the let me see. I think I have a picture of a turbulent boundary layer right next to this one. Oh, no, boundary layer thickness here. This one is just an actual sort of experiment where they use fluorescent dye and a laser sheet to be able to image instantaneous streak lines, and basically you're seeing that instantaneous picture of a turbulent boundary layer where you have the plate at the bottom, and basically you have all sorts of different eddies, small, big and small, that are created by all the turbulence, right? And so these ones, the eddies, actually means that there is increased momentum transport. So the fluid can adjust much more quickly to the no-slip boundary condition because momentum quickly at a distance from the plate gets transferred from different layers of the flow. So the boundary layer thickness is less for a turbulent boundary layer, and the shear stress is larger. For turbulent. So this, I mean, I don't want to actually go too much into details. I just want to give you the concepts of boundary layer because they're important. You can get just a hint of what is implied here. Just the main ideas, okay, of boundary layer.
So then a plate moving through a turbulent liquid would be much more resistant than one moving through a laminar flow.
The drag is going to increase. The drag is going to increase when the boundary layer becomes turbulent. There's more transfer of momentum. Therefore, the fluid adjusts between the free stream and the no slip boundary layer much more quicker. The velocity gradients are much more pronounced, and the shear stress is also larger. In general, those are kind of like the physical sort of description of the boundary layer. That finishes our discussion of the Navier-Stokes equations, and as far as we can do in this course. And the next thing that we're going to do is start a discussion, and we're going to do just a brief introduction to computational fluid dynamics. Let me just give you the motivation for that before you leave today. For the computational fluid dynamics. I was expecting I'll have a little more time today, but that's okay. Let's move. So recall that in the Navier-Stokes equation, which look like this in the vector form, we have, well, recall that this guy is our local acceleration, unsteady term. Recall this guy is the convective acceleration. We have pressure gradient and viscous effects. Right? This you should be able to identify, of course, for the midterm exam. I expect you to be able to identify the terms and understand them in those terms, what they mean. I've dropped out here the weight. Many times we can do that. The effects of gravity and compressibility are negligible in many of the situations we're interested in. So what's tough about this equation is that it's a nonlinear partial differential equation. It's a second order partial differential equation because these terms are second order. They involved second order derivatives, right? So it's a second order nonlinear partial differential equation, and with very few analytical solutions, which basically we've discussed them all in the previous lectures. Very few. There has to be very specific situations of symmetry for there to be an analytical solution. What is a solution, by the way? But what would constitute a solution of this equation? What? Yes. What is the solution that you plug in? What would you have to know? Suppose we have the boundary conditions. And what information do you need to know about the fluid to say, I have the solution in this case? Velocity. First thing we need to know. Right? Very good. Yasmin, very good. What else? So we need to know the velocity field. What else? The pressure. Yes, very good. So this So velocity, field, and pressure, that's what constitutes a solution. We're assuming that it's incompressible, constant density. We're neglecting compressibility for the time being. If it was compressible, we could have an equation of state, and that relates perhaps the pressure and density. So we could manage that. But the velocity field, which is a vector quantity, so it's three unknowns really, u, v, and w, and pressure. So all of those are knowns. Now, in fact, in more complex situations, these Navier-Stokes equations could be even coupled with heat transfer or chemical reactions. If suppose an internal combustion engine, chemical reactions and heat and a lot of stuff going on there, and it's all coupled. So things can get even more complicated. But for the time being, suppose this is just what we're looking at. So to obtain a solution, we need the initial and boundary conditions. Perhaps initial conditions are also required if the thing is transient. Boundary conditions and initial conditions. So why, this is the motivation of why CFD is needed. Well, so remember that we have in general no analytical solution in terms of velocity and pressure that are applicable to the Navier-Stokes. So we are left with only basically two options, right? Experimental, because analytical is no good, right? In general, we already discussed the situations where an analytical solution is possible, there are not many. So in general, we're only left with two options, experimental or computational. So perhaps you think experimental would be the first thing to try. Why would you not do experimental? Suppose that you wanted to study, say, the flow in the breathing tract of humans, and you want to determine, say, if a particulate that is toxic is going to reach the alveola or not. You want to study the effect of breathing particles of, say, different sizes in the human airway. So clearly we cannot do experiments in this situation, right? Because, well, first of all, it would be unethical to do experiments with humans. And even if we could do experiments, what would you see? You can't really see what's going on. I mean, even if you did experiments with somebody, how would you collect data? It would be kind of impossible. So here's already two reasons why you would need CFD. First, because experiments are too dangerous or hard to carry out or unethical. And second, with CFD, you have the possibility of going inside this system and somehow obtaining information about the velocity field and the pressure field. This is what constitutes a solution, and magically going inside this system, right, and getting those values that would not be possible to observe. Other reasons that you need CFD. Testing many scenarios, answering what-if questions. Perhaps it's faster than doing experiments. This movie is for a simulation of a swimmer who is wearing the Speedo suit. It happens that CFD was used very successfully in this case to study the flow around the swimmer and determine which were the areas where drag was more important and be able to design the Speedo suit according to those results. And it was completely done by computational simulation. And later on, the experiments were made with the already designed suit. And the experiments actually demonstrated that this was the suit that produced the least drag known until then. So the experimental results only confirmed the simulation, the design based on simulation. Because the use of CFD allowed the designers to answer what-if questions and test many different options and parameters and measure the results. And of course, in situations of design of mechanical systems, you may have as well need to span many parameters. And if you were going to do experiments in that situation, you'd spend years of trying to cover the whole range of parameters that you would need, and perhaps with the simulation, you can quickly change those parameters in the equations and run the simulation again and quickly span the parameter range, which takes you to a sweet spot for the design. So these are the reasons. And finally, the other reason is entertainment. And this is actually a simulation done by a professor in Stanford University who might be the only computer science professor with an Oscar award. He may, I think he is. A professor of computer science who did this simulation and some other simulations that were used in, very realistic looking, isn't it? Other simulations that were used in Pirates of the Caribbean and so on. And he was given the Academy Award in February 2008 for his work in entertainment. So the myriad applications, the final one before I let you go to your next class is this case of what's called the artificial nose. It was a study done by taking MRI scans of a canine nose, and they did a CFD simulation of all the flow inside this very complicated labyrinth of passageways, and were able to identify the place in the nose where the a place that was very important for the capacity of the nose of a dog of detecting like really trace amounts of a substance is thanks to this complicated flow that they have in their nose. So of course these guys were interested in doing a artificial nose for applications, military applications, and so on.